and catch us up to speed with enthalpy, remind us of a few things. The dry lab is going to be really good practice with calculating delta H. Okay, anybody remember what delta H is? Change in enthalpy. That's what we looked at calculating last week. We ended with this slide right here. And we learned by looking at a chemical reaction, here we have CH4 and oxygen, O2, making CO2 and water. This is a combustion reaction, which we know produces heat. So we see that delta H is negative. Overall, the system, the reaction is losing energy. It's giving off heat, it's giving off energy. We would feel that if it was done in a test tube, the test tube would get hot. And because this amount of heat give off is associated with this particular balance reaction, we can write a relationship for that with any reactant or any product. I could say that for every 2 moles of H2O, that, or I should write moles there, for every 2 moles of H2O, that is associated now with negative 213 kcals of energy for this reaction. I could do that with any of the reactants, looking at the coefficient and what the chemical equation or the chemical formula is. So we looked at how to write relationships like this, and then we worked problems like this, particularly with the CH4, 1 mole of CH4 to negative 213 kcal. And we use that as a conversion factor to calculate amounts of energy. And there will be a problem like that on the dry lab that you'll do for good practice, okay? So I want you to be able to look at a reaction, make a relationship like this, what we just drew out, and then use this as a conversion factor. If I said, okay, you have 4 moles of water, how much energy would be produced? Be able to calculate things like that. All right, but let's pick up with these 2 statements down here, because I don't think we got to these last Thursday. I'm going to read them, and we're going to decide. There's a part we got to decide about, and then we're just going to move on from enthalpy after this. But it says in an exothermic reaction. So remind me, in exothermic reaction, is your delta H negative or positive? Exothermic, is delta H negative or positive?
Negative.
Negative. Okay, so if we have an exothermic reaction, we have a negative delta H. Overall, the system, the reaction is giving off energy, just like this combustion reaction up here. So if we have an exothermic reaction, the products, are they more or less stable? Remember, the whole point of all of this talk is to become more stable, right? And when we have an exothermic reaction, are the products more or less stable than the reactants? What do y'all think?
They're going to be more stable if it's a negative reactant.
Okay, Kenethia says more, Ashlyn says more. Anybody else? Anybody disagree? Play devil's advocate? That's correct. They're actually going to be more stable because they're lower in energy. If the reaction has given off energy and released energy to the surroundings, then the products have less energy than the reactants had, okay? So the products are more stable because they have less energy than the reactants. Therefore, the reaction is favorable. Remember the word favorable and spontaneous we can use interchangeably. So the reaction will be spontaneous, the reaction will be more favorable, okay? But remember, when we started last Thursday, one of those beginning slides, we said enthalpy is only one of the pieces to the puzzle. We said, the whole question we're asking with chapter 7 as we're talking through these things is, how do we know if a reaction is going to happen? Our body, is one giant, everything about our body is chemical reactions. There's millions and billions of chemical reactions happening in our body all the time. And our body is constantly having to make these decisions. Are these reactions energetically favorable or not? And if they're not energetically favorable and our body still has to get it done, then we've got to find ways to do that. So enthalpy is just one of these pieces. So we're going to look at the second piece today. All right. Enthalpy is not the only factor when determining the spontaneity. So what is the second piece? Also pause real quick. Here's 2 more problems for practicing enthalpy. If you want more practice, I'm going to skip over these slides for right now. And when we get closer to chapter 3, we'll come back and we'll do these for review and for practice. But if you want to go ahead and attempt them and try them and kind of test yourself, how much did you retain about how to estimate the delta H? They're great problems to practice, but we will come back and pick these up as review before the exam, okay? So I'm going to skip over them for now, but here's the slide I wanted to get to. And actually, before I read this, to summarize enthalpy so far, what we have learned about enthalpy is this. A negative delta H, this is favorable. Okay, a reaction that has a negative delta H tends, I'll say tends, because it's not necessarily always, but tends to be spontaneous. All right, a positive delta H is unfavorable. And these reactions tend to be non-spontaneous. All right, so with a negative delta H, that's favorable. The reason is the products are more energetically stable. All right, so that, if I could summarize what we've learned so far, that's the summary. That's the overall big picture part of enthalpy. Okay, so with that, now that we've just addressed that, let's actually read this question, and then we're going to consider what is typed right below it. The question says, are all exothermic processes spontaneous? And are all endothermic processes non-spontaneous or not unfavorable? Okay, can we say, well, if they tend to be more favorable when they're exothermic, can we say all exothermic reactions are favorable and all endothermic processes are unfavorable? Before we answer that question, let's actually look at what's happening just down below. And tell me if you agree or if you disagree. I just want you to think about this. If you sit ice on a plate, and let's say that plate is at room temperature, it will absorb heat and melt. What do you think about that? That'll happen, right? That seems kind of like a common sense statement, okay? Yeah, but the question is, what kind of reaction is this? What kind of process is this? Is this an exothermic or an endothermic process? I want you to think about this. What we have is water as a solid. We know that is ice. And we have water going to a liquid, and this is liquid water, okay? So if you sit it on a plate at room temperature, it will absorb heat and melt. So the key word here is absorb. Absorb heat. What kind of process absorbs heat overall? Overall, it's absorbing heat. Is this exothermic or endothermic? What do you guys think? Endothermic question mark? What do y'all think? Anybody agree? Kanithia in the chat says endothermic. Do you think ice melting gives off heat? That would be exothermic. Do you think it says it absorbs heat? So Dakota says endothermic as well. And that is correct. Okay. This is endothermic. And endothermic is a positive delta H. Overall, it's absorbing heat. Now, the second question is this process spontaneous? Meaning, do I have to do anything for that to happen? Or will it just naturally happen? Do I have to pop it in the microwave? Do I have to put it on a stove and turn the burner on? Or will ice just spontaneously melt? What do y'all think?
It'll just melt.
It'll just spontaneously melt. Okay, now why are we talking about this? Right, so this is favorable. Okay, if it's spontaneous, it's favorable to do it. So why are we talking about this? Well, the answer, if we go back to this question up here, then the answer to this question is no. Are all exothermic processes spontaneous? No, because we have an endothermic process right down here, ice melting. It's endothermic and it's spontaneous, okay? So all I'm trying to say is we cannot necessarily just look at delta H and say, oh, if it's negative, the reaction is going to happen. Oh, if delta H is positive, the reaction will happen. It's more complicated than that, okay? I wish we could simplify it to that, but we can't. So there's another piece to the puzzle that we have to consider before we answer the question, how do we know a reaction will happen or not? And the second piece to the puzzle is entropy, okay? Entropy. So what is entropy? Well, first off, entropy is S. We abbreviate it with an S. So enthalpy and entropy are spelled very similarly. They sound similar, but make sure you know the difference in the spelling, you know the difference in the pronunciation, and you know the difference in the abbreviation. Okay, entropy is S, enthalpy is H. Entropy is a measure of disorder in the system, and the system is, our system is the reaction, the chemical reaction. Okay, how much disorder? So how the heck do we measure disorder? Well, we're going to get there. I'll explain that. First, too, also, just like with enthalpy, we can calculate a delta S. As a reaction goes from reactants to products, we can calculate delta S. And what are the units on delta S? They're right here. Calories per mole Kelvin. Calories per mole Kelvin. Those are the units for delta S. Now, these are a little bit different than units that we saw for delta H. Can anybody remember a difference or think of a difference between the units of delta S and delta H? What's one difference that you may notice right off the bat?
One was in calories and the other one's in kilocalories.
That's right. Delta S is in calories. Delta H was in kcals or kilojoules. It can all be done in kilojoules as well. Now, which one's bigger, a calorie or a kilocalorie? Kcal. Thank you, Brendan. Dakota, calorie is smaller. Brendan got it right. Kcal is larger. A kcal is 1,000 calories, okay? So what that means is the units for delta S are much smaller, okay? So delta S has units of cals, and this is smaller than delta H. So changes in delta S, why are we using calories instead of kcals? Changes in delta S tend to be smaller, okay? Changes in, I'm just going to write that, changes in entropy tend to be smaller scale. All right, that doesn't mean they're not important. They're just not as large as changes in delta H. All right, so that's one difference. The other difference, does anybody notice another difference?
Using temperature.
Yes. Look right here, we have Kelvin, K, Kelvin in our units. So what this means is delta S is temperature dependent. All right, because we have units of Kelvin in the denominator. And to prove this point, go back to the ice thing up here. Ice sitting on a plate and melting. Sure, that will happen at room temperature, but what if that plate is in the freezer? Will it melt then? No. What if it is in the refrigerator? It will still melt. The process will be slower, but it's definitely temperature dependent. Okay. So there we go. Now, this last statement down here says processes for which delta S is positive tend to be spontaneous. And remember, we can always substitute that word for the word favorable. Okay, spontaneous or favorable. So up here, where was it? Right here. For delta H, it's a negative delta H, where processes tend to be favorable. But for delta S, for entropy, it's a positive delta S that tends to make a reaction favorable. And I know this is kind of, the pieces are all over. We're going to bring them all together in just a minute. But just keep these straight in your head. So let's talk a little bit more about entropy. How do we actually measure a change in disorder? There's two things to consider. This is just the definition again. And these statements that I'm about to read are kind of redundant, but just so that we keep it straight. When delta S is positive, entropy is increasing, okay? Disorder. Remember, this is disorder. When delta S is negative, entropy decreases. Disorder decreases, okay? So here you are becoming, on this one, you're becoming more ordered, All right. Okay, so now that we have those things stated, I want you to look at this figure. This is actually straight from your textbook. There's two things to consider when we're measuring disorder. One, what is your state of matter, solid, liquids, or gases? What do I have on my reactant side? What do I have on the gas side? If you guys remember, very first week, I believe, of class, we actually drew a picture of solids, liquids, and gases. I'm going to do this. A solid, we know, we said is pretty ordered. Okay, solid particles and molecules that are in a solid state of matter, they're very close together. And especially for like ionic solids, they're arranged in like a crystalline structure. Not for all solids, but I'm going to draw a picture. And let's pretend these red spheres are just molecules. And this is how they may look in a solid. They would kind of be close together, bonded to one another. There's forces at play between the spheres that are holding them together. They don't have the freedom to move around, and they're kind of ordered. Okay, so this one is most ordered. A liquid we know is different. Molecules in a liquid, they're further apart, and we drew some lines because they have the freedom to flow. They can move past one another. Okay, so this is more disordered than a solid, right? And gases, we said these particles are furthest apart, and they are just zooming past one another at a very high rate of speed. They can go wherever they want. They are not bonded to one another. They're not interacting with one another the way particles in a solid are. So this is most disordered. Just inherently. Inherently, these states of matter have these levels of order and disorder. So as you take something and you melt it or evaporate it, you're becoming more disordered. If you take a substance and it's a gas and you condense it or you freeze it towards the state of matter that's a solid, you are becoming more ordered. Okay, questions on that? Make sense so far? Okay. The other way to measure entropy, so that's why this figure, if we read the box here, entropy increases as you read the figure from left to right. Okay, that's why the arrow is saying entropy increases as you go across the figure this way. All right, also entropy increases if you have fewer moles of stuff on your reactant side and you end up with more moles of stuff on your product side. We'll look at some examples, okay? So for example, what would be an example of that? I'm thinking about the kinds of reactions we learned. Combination, decomposition, single, double displacement, or combustion. Can anybody think of one that's a great example of going from fewer moles of stuff to more moles?
Decomposition.
Decomposition is exactly right. So if you have something like a reactant, AB, and it breaks down into substance A and substance B, I could have 1 mole of reactant and end up with 2 moles of products. Does that make sense? And so you're more ordered on the reactant side and you have more disorder on the product side. Okay, so that's exactly what the bottom portion of this figure is alluding to. Now, if you read the figure from right to left, the exact reverse of these processes. So, for example, a combination reaction we know is the reverse of a decomposition. A combination reaction says A plus B makes AB. So we have more moles of products this time on the reactant side, and we're making fewer moles. So we're becoming more ordered. And in that case, entropy is decreasing. All right. So this is a combination, or synthesis was the other word for that reaction. And this was decomposition. And I actually should, I should move this up here because this actually matches the arrow that is up here where it says entropy is increasing. Okay. Any questions so far on that? And I'm going to erase the words reactant and product right here because you don't always have fewer moles on the reactant side and more moles on the product side. That was just if entropy decreases, or sorry, increases. All right, so to put this to this, a good example, there's several analogies you could think of. Personally, I think of my house. Okay. Anybody relate to me? You can clean it one day and then it's like you turn around 2 hours later and you're like, did I even pick my room up? Especially when you have small humans running around your house. I constantly have teacups and somehow my measuring spoons from the kitchen end up all over the floor of our living room. So disorder is a constant battle at our house. But the example that the book gives you is with this stack of cards. Obviously, if you have cards stacked together, that is very ordered and arranged. If you've ever played 52 card pickup, that's I don't know why we have family members that decide a good gift for a 2-year-old is a deck of cards. I'm serious. She does not know how to play cards. She does know how to scatter them though. So this side is disordered, right? So this is the example. Entropy is increasing here, okay? Positive delta S for processes like this. So if it helps you to think of examples outside of molecules, that's what we're talking about. We're just talking about order and disorder. If you have dogs that like trash, they do the same thing, okay? This is another reason I don't have animals in my house, okay? I'm not anti-dog. I just don't. Dogs do that for sure. I'm sure cats do stuff too. All right, let's actually look at this reaction. N2 and 3 moles of H2 gas make 2 moles of NH3. NH3 is ammonia gas. And I want to know, is entropy, delta S, change in entropy, increasing or decreasing here? Are you becoming more ordered or are you becoming more disordered as you go from reactants to products? What do y'all think?
More ordered?
More ordered. Okay, Aubrey says more ordered. Bailey says that disorder. Do you mean disorder, Bailey, is increasing or order is increasing? You wrote increasing. You think entropy is increasing, I guess? Order is increasing. Okay. So disorder is decreasing because remember, entropy is a measure of disorder. So always try to, if you can understand it from the viewpoint of order, then you got to flip it and say, okay, what is disorder doing? So disorder is decreasing. So far, that's what the consensus is. And y'all are correct. Okay. We have 1 mole of nitrogen gas. There's an understood 1 plus 3 more moles of hydrogen gas. We have 4 moles of gas on the reactant side. And we only have how many on the product side? 2. All the products and reactants are gases. So we actually don't have to worry about changes of state, solid, liquid, or gas, but we do have to address it. Okay, what's happening with regards to the number of moles? That's really how we're assessing this one. But there's more than one way to do it, especially if you have if not everything is the same state of matter, if you do have solids and liquids and possibly gases too, all in one reaction. So definitely disorder is order is increasing, disorder is decreasing. So delta S should be negative here. You're becoming more ordered. You're becoming less disordered. So delta S is negative. Questions on how we just did that?
Why don't we use the word organized?
That's a great question. If it helps you to think about it that way, that's totally fine. It's just that the chemistry verbiage is with the word disorder. So if you want to think about being ordered as being organized, that's perfectly fine if that helps you. But just make sure that you also know how to address it from the state. If I ask you about disorder, that you know then how to answer that question.
Also, if there's a measure for disorder, is there a measure for order?
They're kind of one and the same, because if you know what's happening from the standpoint of disorder, then what's happening from the standpoint of order is just maybe the same value but the opposite sign. Does that make sense? Like if it's a negative number that's describing disorder, then it would be the positive number that's describing order. Does that make sense?
Yeah.
They're kind of one and the same in a weird way. Because order and disorder are opposite processes, right?
Yes.
Okay. I hope, did that answer? I don't know if that answered your question very well, but I've never been asked that either regarding this, but that's okay. All questions, there's no silly questions here. Okay, so I actually have a poll question. So I'm going to run a poll for these. I want you to take a minute. I have 3 reactions here, and I want to know, does entropy increase or decrease? That's the poll question. Okay, does it increase or decrease? And I want you to put all your answers in. And don't worry if you get it right or wrong. Honestly, right here, it just doesn't matter. I just want you to think and give me your best shot, and then we'll talk through the correct answers afterwards. I'll give you about 2 minutes. So I'm going to launch the poll. Wait, sorry, this is the wrong one. I have multiple. This is polar, but it's a very old one in the poll. Let me pick the right poll. There we go. Launch it. Okay. So there's your poll question, and I'm going to give you about 2 minutes. About almost a minute and a half in, so take maybe another 30 seconds. Sorry, hold on. There we go. All right, it's been about 2 minutes. We're only 83% voted, but if you haven't voted yet, it's okay. I'm going to end the poll and we're going to talk about these. So share results. There they are. So let's look at number 1. Thank you, Bailey. She said, bless you. Number 1. Most people said that disorder, entropy, is increasing, so that we're becoming more disordered, and that is absolutely correct. Okay, if you look at number 1, you have 2 moles of a solid, which we know is inherently the most ordered state of matter between solid, liquid, and gas. So we're pretty ordered, and we only have 2 moles. We have 1 single reactant, and this is definitely a decomposition reaction. Okay, you have sodium bicarbonate decomposing into sodium carbonate, water, and CO2. So we have 3 different products on the product side. So that's obviously you have more disorder just because of that. But you're also, if you're looking at the changes, you have more. You're going from fewer moles of stuff to more moles of stuff. But then also you're going from solids and look, you're making liquids and gases as well, which those states of matter are inherently more disordered. So for sure, delta S is increasing here. Disorder is, we are more disordered. Okay, so disorder is increasing, which is why delta S is positive. Entropy is increasing. Okay, let's look at the second reaction. Most people said that delta S is decreasing. Okay, delta S is decreasing, so that we're becoming more ordered in a sense. Let's look at it. Well, the first thing I notice is that we have gases only on the reactant side. Both reactants are gases. How many moles of gas do we have total? Well, we can add those up. We have 3 moles of gas total between our 2 reactants. On the product side, one product is a gas, the other is a liquid. So we have 2 reactants and 2 products, and we have 3 moles of stuff okay, substance on either side. So we can't necessarily judge it from the fewer moles or more moles idea, but we can see that we're going from a gas and we're making a liquid. Okay, we know a liquid is inherently more ordered. So here we only have 2 moles of gas, or sorry, 1 mole of gas and 2 moles of liquid. And liquid, because it's more ordered, we are becoming more ordered here. So disorder is decreasing and delta S is negative. So the majority got it right that disorder is decreasing on number 2. Questions there? Okay. All right. The third one, most people said that it is again decreasing. And if you were actually paying attention, one slide ago, we did this exact reaction up here. So this is a combination reaction. And a combination reaction, if you remember, entropy decreases when you have combination reaction. Okay, that's why we wrote it on this side. You're becoming more ordered. You have 4 moles of gas is what we wrote on the reactant side, 2 moles of gas on the product side. You have 2 things combining to 1. So delta S is negative as well. Okay, questions on that? Okay. Well, now that we have, this is kind of the end of entropy. So we talked about enthalpy. We took a lot more time on enthalpy, a whole day. We've actually finished describing entropy now. And these are 2 pieces of the puzzle. So we're actually going to put these together now and kind of see the bigger picture. So what we have learned so far is that a reaction is favorable or spontaneous when your delta H is negative. That's an exothermic reaction. We said that one's favorable over an endothermic reaction. And we said when delta S is positive, when disorder is increasing, that is also favorable. Reactions tend to be spontaneous when you have these kinds of signs on your delta H and delta S. So what actually happens when you have these 2 things combined, when you have a reaction that is exothermic and you're becoming more disordered, that reaction is always spontaneous. Or I should say always favorable. And you can write always. Okay, always. It will always happen. You do not have to do anything to it. Once it gets started, it will go to completion on its own. Now, what if we have the opposite of this? What if we have a positive delta H, which is endothermic? Overall, the reaction is absorbing heat, like the ice melting. Okay, if we did a reaction like this in a test tube, it would feel cold to us because it's pulling energy in. We would feel the absence of that energy, absence of heat. So positive delta H and a negative delta S. Disorder is decreasing. You're becoming more ordered. This kind of reaction will never be spontaneous. Okay, it's not favorable. It's not going to happen on its own, at least. Now, we can also have other combinations of delta H and delta S. So what if they're both positive? What if they're both negative? If these are the cases, then we actually don't have enough information just from looking at the signs of delta H and delta S. We actually don't quite know unless we do some more digging if it will be spontaneous or not. So what do we do in these cases? We are going to use an equation. What equation are we going to use? It's called Gibbs free energy, okay, which, if you notice, is the title of the slide. So I'm going to introduce this equation to you. It is once you understand the terms of it, which you already know, delta H and delta S, it's just a plug and chug type of thing, okay? So don't be overwhelmed by the terms. There are a few things to know about it, and we'll do several practice problems with it. But Gibbs free energy says this: delta G, which is our new term, this is Gibbs free energy, delta G, equals delta H, this is our enthalpy term, minus T. What is T? T is temperature. And one thing to know about the temperature here is it must be in Kelvin. Don't ever do it in Celsius or Fahrenheit. Times delta S. And this is our entropy. Okay. So delta G equals delta H minus the temperature times the entropy term. And temperature has to be in Kelvin because remember, in delta S, we have units of Kelvin. That's why temperature has to be in Kelvin. Another thing, the Kelvin scale it doesn't have negative numbers. There's no such thing as a negative Kelvin. So you can never plug in a negative temperature. On Celsius and Fahrenheit, you can have negative temperatures. So that's another check to make sure you're in the right units with temperature. If you have a negative Celsius temperature, you're in the wrong units because you cannot plug in a negative temperature in the Kelvin scale. So this should always be a positive value, okay? Unless it's 0. All right, so there's our equation. And once we know delta G, first off, what is delta G? What is it about? Well, delta G directly tells us if a reaction will happen or not. And remember, that's the overarching question we've been asking this whole time. How do we know if a reaction is going to happen or not? Again, to relate this more to the health sciences, because honestly, for me, this is the hardest chapter in our whole semester to help you see like why it's important. All right. A lot of you just see the math of it and why am I doing this math? I'm never going to have to do this math again in my life. And you may be right. But our bodies think this way, believe it or not. And so to help you understand your body better and to appreciate it, I hope you're having a greater appreciation of your body after this. The body reacts and it does chemical reaction in terms of what's energetically favorable. So this is a more complete table down here, but delta G, the sign on delta G, whether it's negative or positive, directly tells us if a reaction will be spontaneous or not. So directly determines spontaneity. Is that how you spell spontaneity? Maybe it is, maybe it isn't. But delta H and delta S indirectly tell us, okay? Together they can tell us, but on their own they can't tell us. Delta G is more powerful than the both of them. It can directly tell us. So if we look at this table, this is the same table that we had above. It's just got a column over here on the right side added for delta G. And if delta G is negative, you can directly say, oh, that's a favorable reaction. That reaction is going to happen. If delta G is positive, you can say that reaction will never happen just from looking at the sign. You didn't even have to know the number of it. Just the sign tells you. Again, columns 3 and 4, if your delta H and delta S have the same sign, well, then we have to actually use this equation and calculate our delta G and then make a comment about whether the reaction is favorable or not. Okay. So I want to introduce just a couple things about a negative and positive delta G before we move on. Okay, why do they directly tell us any information? Well, first off, we have names kind of like endothermic and exothermic that were associated with the sign of delta H. If you have a negative delta G, this is called exergonic. A reaction with a negative delta G is known as an exergonic reaction, and a reaction with a positive delta G is endergonic. Okay, exergonic and endergonic. Exergonic reactions are spontaneous, they're favorable, they'll always happen. Which is the next statement. The reaction is always spontaneous if it's exergonic. The reaction is always non-spontaneous if it's endergonic. Energy overall is released in an exergonic reaction. Energy is overall absorbed in an endergonic reaction. And then lastly, the products are lower in energy than the reactants in an exergonic reaction. Thus, they are more stable. And vice versa, for endergonic, the products are higher in energy, thus they are less stable. Okay. So that's delta G. And this is kind of a lot. If your head is swimming right now, it's okay. I expect it to be. We are going to work some problems, and I hope that will help solidify and help you process everything we just explained, because we just explained a ton of information. So we're going to practice calculating delta G. I promise on exam 3, you're going to have a calculate delta H problem. You're going to have a calculate delta G problem, okay? But again, the math concepts are the same. Once you know how to do them, that's it. You plug in your numbers and you go. So let's look at this. We're still talking about ice melting here, okay? So that's our process. We have ice making liquid water. And we're given two values. We're given our delta H and we're given our delta S. Now, we want to know what is delta G at 3 different temperatures. What is delta G for this process of ice melting at negative 10 degrees Celsius, 0 degrees Celsius, and 10 degrees Celsius? So all we're going to do is we're going to plug numbers in. We're going to calculate delta G. But there's 2 things we have to check before you ever plug in and calculate delta G. Can anybody tell me what's one thing you can automatically see we're going to have to do?
Convert Celsius to Kelvin.
Yep, remember I said your temperature always has to be in Kelvin. So we're going to real quick convert these temperatures to Celsius. So that's step number 1 is always check that temp is in Kelvin. And if it's not, convert it to Kelvin. All right, let's do that really quick. Negative 10 degrees Celsius. Does anybody remember how do we convert to Kelvin? What do we do? It's real simple addition. It's not the 9/5. Yes, Brendan, but you guys are forgetting your decimals. Come on. It's 273.15. There we go. So add 273.15. What do we get? We get 263.15 Kelvin now. For 0 degrees Celsius, that one's real easy. And for a positive 10 degrees Celsius, okay, boom. So we've got all our temps in Kelvin now. Don't forget that step. If you forget that step, you will miss a majority of the problem. Step number 2, if you look at your delta S and your delta H, remember the other difference in the units we talked about is one is in kcal and the other is in calories. We have to make them match. So what I always do is I take my delta S and I convert it to kcals. So that is step number 2. Convert delta S from calories to kilocalories. Anybody remember the relationship there? How many calories are in a kilocalorie?
1,000 calories.
That's correct. Don't flip those. Some people accidentally get them mixed up. 1,000 calories and 1 kcal. So let's go get our delta S value. What is it? It is 5.26. And we want units of calories to cancel. So I'm going to take this relationship that I wrote just above it. I'm going to plug it in with 1,000 calories on the bottom and 1 kcal on top. And all I'm trying to do here is cancel calories and convert to kcals. I do not lose my denominator, moles per Kelvin. That part stays with me. So the final units that I get here, so you'll do 5.26 divided by 1,000. You'll just move the decimal 3 places to the left. Now my units are kcal per mole Kelvin. And I prefer that you write it this way with one number on top and the others on bottom, okay? Instead of writing them like this with the slash and it all in the same line. It will help you mathematically, I promise, if you will separate top and bottom just like a fraction. All right. Okay, so we've done our 2 steps. Now, because our units on delta H and delta S match, regarding the energy part, they're both kilocalories. And because everything's in Kelvin, now we just plug stuff in. Oh, I want to shrink this down. Okay. Give us some more space. You should have seen me this morning. I literally left like a tiny portion of the slide for the delta G calculations. But I'm smarter this time. All right, number 1. So we're about to calculate delta G. We're going to do it for the negative 10 degrees Celsius. So this will be for negative 10 degrees Celsius. So we're just going to plug everything in. Here's the equation. So we're going to say delta G equals, what is our delta H? Here it is right here. We're just going to plug it in. 1.44 kcal per mole. And we're going to do minus, now we're on this part, T delta S. And our temperature in Kelvin is 263.15. And I like to put brackets around the T delta S part so that in my calculator I put it all in parentheses so that I know things are multiplied and added correctly. And this is going to be multiplied by, I want to scoot all this over. Why can't it just all grab it all at once? Okay, and my delta S was 0.00526. Whoops. There it is. Okay, that looks like a lot, doesn't it? All in one equation. So now notice what happens in the parentheses part over here. I have Kelvin right here in my temperature, and I have Kelvin on the bottom of my delta S term. Remember, this is delta S and this is temperature. So Kelvin actually cancels because I have it on top and bottom, which is great because then I'm left with kcal per mole. And over here on delta H, I now also have kcal per mole. So I actually can add those units or those terms because the units are the same. Anybody want to do the multiplication and then do 1.44 minus that portion in parentheses and tell us what our delta G is overall? So you should do 263.15 times 0.00526, get a number, and then do 1.44 minus that number.
I got 0.055831.
0.055831. We'll just say 8. We'll stop there. And
Okay.
units are kcal per mole. Okay, so the question is this a positive or a negative delta G?
Positive.
Positive. It's barely positive. It's a small number, but it is positive. And so that answers the question. And is this spontaneous or not? Remember, a positive delta G is non-spontaneous. So ice will not melt at negative 10 degrees Celsius, in case you were wondering. But if we increase the temperature to 0, would it melt? We'll determine if our delta G is negative or positive. If it's positive, that's not a spontaneous process. It's not going to happen. So the ice here won't melt. Okay, 2. We're going to do it now at the 0 degrees Celsius. So we're literally going to do the exact same thing. So I'm just going to copy. Someone taught me how to do this. I forget who. Everything should be the same. But this time, when we plug in the temperature, it should be 273. So I'm just going to erase this one little number. It should be 273.15. And they'll say times the 0.00526 kcal per mole Kelvin. This is kcal over here on the very edge. Sorry, it's kind of smushed. So literally exact same equation, exact same delta S, exact same delta H. Your temperature has just increased. So we're kind of asking the question, at some point, if we keep raising the temperature, will our delta G become negative? Will the reaction become spontaneous? So if somebody wants to calculate that and tell us what delta G is.
I got 0.0032 kcal per mole.
So still positive, but it's closer to, we're headed the negative direction. And I have very little room here, so I'm going to squeeze this number down to give us some more space. How am I going to fit this in? We'll say number 3. Same equation here. This time you're just plugging in 283.15, right? That was our third temperature. For the positive 10 degrees Celsius was 283.15 Kelvin. So do the exact same equation. Go ahead and throw it in your calculator while I write it all out. Maybe you can beat me. And what do you get for delta G this time?
Negative 0.0494. Excuse me. Get the hiccups.
We'll just say 0.049. And again, kcal per mole. So what we just did this with 3 temperatures, and this seemed like a lot of work, and it was. But what we saw is as temperature increased from 263 to 273 to 283 Kelvin, as we kept raising the temperature, eventually we got a negative delta G. And what this means is here the ice will melt. So the sign of delta G, the whole point I want to kind of bring to the surface right here, the main point is that the sign of delta G directly tells you if a reaction is spontaneous, okay? So this is spontaneous. In other words, it's favorable. These up here, these delta G's, because they're positive, these are I'm going to abbreviate, non-spontaneous and non-spontaneous. But when you have a negative delta G, that reaction will happen, okay? You can directly look at the sign of delta G and know. Delta H and delta S just contribute to getting your delta G, okay? We're going to do one more problem, and then I think I wanted to save like the last 10 minutes of lecture. So we'll be done right after this. Okay, this last reaction here says carbon and water make CO2, or sorry, CO, carbon monoxide. That's bad stuff, right? And hydrogen. Looking at this reaction, does entropy increase or decrease? Does entropy increase or decrease? Is delta S positive or negative? Well, look at your reactant side. We have a solid and a liquid. 1 mole of solid, 1 mole of, it looks like it's balanced already. So it's just coefficients of 1 across in front of everything. On the product side, we have 2 products as well, but they're both gases. So here it's not that you have fewer moles and less moles, but it's just that inherently we have more ordered reactants, more disordered products, because things that are gases are inherently more disordered. So disorder is increasing. Over here we are more disordered. All right, so delta S is positive. Questions on how I arrived at that conclusion? Again, I know it's kind of probably really stretching you to think in these new terms, but hopefully with practice, you can become more comfortable with it.
I kind of have, okay. So can you just so do you get that from the solid liquid to a gas and a gas?
Yeah, remember the figure? Let me go right back to that figure, Aubrey. Right here. As you go from a solid to a liquid to a gas, from reactants to products, if your reaction looks like that, you have solids or liquids on the reactant side and you have gases on the product side. Here it says entropy is increasing in a process like that. Does that make sense? So hopefully you can rely on that figure to help you with these things. Okay, second question says if delta H is negative 31.3 kcal per mole and delta S is positive 32 calories per mole Kelvin, Is the reaction spontaneous at 27 degrees Celsius? It's not necessarily asking us to calculate delta G just yet. Remember, we can go look at the table. Let's go look at the table. We have a negative delta H and we have a positive delta S. Let's go see which row that match. Negative delta H, positive delta S. Negative delta H, positive delta S matches row 1 right here. And when you have those two together, that reaction will always mathematically give you a negative delta G. That is always spontaneous. Okay, so hopefully when you're given stuff like this, you can just go look at this table and see which one it lines up with and say, is the reaction spontaneous? Yes, it is. Always. We will get a negative delta G. Now, we don't know what the value is yet, which is part number 3, but we will get a negative delta G. And so to calculate it then, all you would have to do, step number 1, we're almost done, I promise, is you convert your Celsius to Kelvin. And you should get 300.15 Kelvin. Step number 2 is you convert your delta S to kcals. And remember to do that, you're always just going to divide by 1,000 calories on bottom for every 1 kcal. So 32 divided by 1,000 should give you 0.032 kcal. I know I'm flying right now, but I'm just trying to get this down for y'all so that we can actually chat like I said I wanted to. Then you just go plug these in and you get your delta G. Okay, if somebody wants to calculate it and tell us the answer, that's great. I'll write out the equation and then I'm done. I won't even calculate it. There's our delta H, because delta G, here's our equation right up here. I have it for us. Delta G equals delta H minus, and then I put it in parentheses, the temperature 300.15 Kelvin times, not divided, not add, not subtract, times the delta S, 0.032 kcal per mole. Oh, I forgot a 2. There it is. Okay. I bet somebody will put it in the chat in just a minute, so keep an eye out for that. See if you get the right answer. But, we need a brain break after this. That is a lot. This is a lot of math.
Can you leave that up for a second while you're talking?
Yeah, I'm just going to leave it right here.
Okay, thank you.
Yeah, so y'all can look at that. If you need me to go back to any slides, let me know. I can totally do that. But yeah, this is a lot. And we still have more to go. We got not quite as far as I wanted to get today, and that's okay. There's several more practice problems with delta G. If you notice on the chapter 7 homework, it's a few more questions than normal. Normal I have like 20 to 25 questions on the homework. This one's like closer to 35 because I wanted to give you more practice. It's not that I just want to give you more busy work. It's that this stuff, because it's so math oriented, does take more practice to really get you ready for the exam. So that's why there's a few more questions than normal on your chapter 7 homework. But once we get over the hump of chapter 7, chapter 10 is tough too, but we should be through a lot of the hard stuff. So I was in an interesting conversation the other day, and I think it's good to kind of self-reflect and hear feedback from you guys throughout the semester. I hope I've given some opportunities via the discussion board and stuff like that to get thoughts from you guys. I don't know about you. I'm definitely feeling the wear of everything culminating just as the semester goes along. It feels like work piles up. It feels like I get more behind sometimes as the week goes. But I heard from somebody the other day that works with a lot of college students that they were saying with all the online stuff this semester, I wanted to know, do you guys feel like compared to a normal face-to-face semester, do you feel like this online semester is way more work than normal? Do you feel like it's about equal? Do you feel like it's pretty easy to manage? And I totally expect different people to have different opinions. But how are you guys feeling with the workload overall? And you can comment just on this class. You can comment on all your classes collectively. I would love to. My main concern is this class, obviously. Yes, to me, online, reading the chat. Tiara said yes. I'm assuming that means yes, more work. Devon said same amount of work, but it's harder. And I perfectly agree with Devon. I agree with that. I think it's same amount of work, but it is harder because online, for example, you do your lab assignments with me. Well, then you have to go online and put all your answers in. Normally, you could just hand that in to me and you're done, right? So there's definitely some more work with that way. And I feel like it's more work too because I have to go create those assignments. And then they don't work perfectly and it's frustrating to everyone. Bailey says online is way harder. Ashlyn says, I love online. Some people are used to it. Some people have had online classes. Online is harder than face-to-face. More work plus less structured work time. Bryce, I can see how the work time seems less structured because it's like you're on your own. In a lab, you'd usually always be able to talk to people and ask questions to your instructor right there. Angelina says way more work, not in this class, but other classes. Pray it gets all done. I like taking tests face-to-face better than online. I agree. I prefer face-to-face as well. Harder because reading Sarah's comment, every professor sets up their Blackboard differently and it gets confusing, especially when it comes to due dates. I've heard that as well. And I agree. I agree with all these things. And I don't know if there's a way around it because, you know, I think I've tried to communicate how to turn everything in and when it's due, but I know you're juggling a lot. And so I also have heard different professors set things up differently in Blackboard. I would love some honest feedback. Do y'all feel like this class, when it comes to how things are put on Blackboard, that they're organized or that it's kind of crazy and you just don't know where to look? Because I would love
organized.
Someone says very organized.
Yes, compared to some of my other ones, you can find anything you need to in your class. Absolutely.
I agree with that. Especially because you send out an email at the beginning of the week. And typically like our homework, our quizzes, it's all due relatively like on the same day every week.
Okay.
I like that. I have one class that's like, she opens up a module at the beginning of the week and it's due by next Sunday. And then I have another class that's just, he like gives you all the work and is like, okay, have this known by the next test. But there's like no in between assignments to like make sure that we're like on board. So I always forget to do it when it's not something that I have to do every week. Like I have all these assignments written down in my planner, you know, to do. And since those aren't like due every week, it's hard to remember to do that until it's the week of the test. And I'm like, oh crap, I have 4 chapters of a book to read.
Oh, so you like having smaller pieces of stuff more scheduled and
I do, but then
almost every week.
whenever I do get really busy and I get behind, it
Yeah.
bites me in the butt when I do have stuff to do
Right.
like on certain days. But I like it more because it holds me accountable more.
Okay. Hey, Kaylin, thank you for this comment. I hate uploading photos. Anybody hate uploading photos? Can I just say I hate it too?
It freaks me out because of time. I'm like, wait, I still have to upload all of these things.
Which is why I try to give you more time. Normally in an online test, I just give you an hour and a half. And so I try to allot an extra 10 to 15 minutes, but I'm sure it still feels rushed. I hate it too. I hate grading online photos. Okay. I'd rather just sit and grade your exams in my lap or whatever. Love-hate relationship with online. It's not much harder, Connor says, just more to manage. Semester was the first online I have had to take. Okay. I always feel like I'm doing something wrong, Hannah. I'm sure it's a lot more to manage. So if you don't write things down, I could see where you could easily get in a tight situation. Your class has been great. Several different ways to teach us. Okay. Because I commute, I'm trying to read all these comments. I'll probably go through and read the rest. There's so much. There's 20 new. Okay, I'm going to go through and read all your comments. We literally have 2 minutes left of class. So I just want to say I wanted to get this feedback from you. And if you felt like you didn't even get to say it in the chat or you were scared to or whatever, shoot me an email because I want your feedback. I'll say this. I do not have the corner market sold on how to do a chemistry class online, okay, or an online class period. So I have been learning. Here's what I wish. I wish I would have been doing the Zoom breakouts with you guys from day one. I feel like, do y'all feel like those have been helpful? If you type it in the chat, I'm probably not going to see it right now. So just you can nod your head yes or no if your video is shown.
Yes.
Good. Well, I'm glad those are helpful. Somebody from the first lecture said that they wished we would do study guides in this course. And I had some questions. I've had study guides when I was a student. A lot of my classes from being a college student, I remember we didn't necessarily get study guides, but I'm not tossing that idea out. But I asked, what would a study guide look like for, what would be a helpful study guide? Do you want me to just list the concepts that you need to go over? Because I feel like we do that, honestly. There's been times I've said, name 10 topics you think are going to be on exam 1, right? So that's a way for you to know, okay, here's the topics I need to make sure I've covered and I've studied before the exam. That's a list. But the comment was, I would love for it to be example problems worked out. Okay. They would love that. And my comment to that was, you actually, if you are doing these problems with us throughout lecture, you do have example problems worked out. They're not all in one nice, neat little PDF for you. And I could put something like that together. But I do try to have review slides or review sessions before every exam. But if anybody has a comment on, here's what I think a helpful study guide would be for this exam, maybe leading up to exam 3, we could try something like that. I could try to provide that. I would love your thoughts as well on that. Anybody other have just, I also want constructive criticism. Okay. I want that. I need it. If anybody has, oh, sorry, my iPad went off. If anybody has any constructive criticism or feedback for me or for the course in general, I'm always open to that. But I want us to take time to kind of reflect and really to check in on how you guys, here's why I really do care. I know chemistry is not easy. I'm not going to sit here and be like, well, you guys should be doing just fine. It takes a lot of effort, and I know life happens and things happen. And so sometimes that complicates stuff even more. So all that to say, we're at time, but I care how you guys are doing in this class and in your other classes. I want you to do well. But if you have any feedback, I want you to have an outlet to share that as well. Okay. All right. Well, hopefully this has been a helpful discussion. It has for